Okay, let's get back to a little math and look at the Clausius-Clapeyron equation. All right, there are two forms of this, and you do not have to memorize this. They'll be on the exam if you need them. The natural log of the vapor pressure is negative delta H vap, the enthalpy of vaporization, over R, the gas constant, times 1 over the temperature plus the natural log of B. Beta is this constant. And why this equation is so nice, because what we can do is we can go into the lab and say we have a gas, and let's measure its pressures at various temperatures. So we put it in a container, take its pressure reading, get its temperature reading, increase the temperature, look at the pressure, get a new pressure reading, increase the temperature again, get another pressure reading, and then if we plot the natural log of the pressure over 1 over T, you end up with a straight line. Because our equation is up at the top here, natural log of the vapor pressure equals negative delta H naught vap over R, 1 over T plus natural log of beta is just Y equals mx plus B. So this is the equation for a straight line, and what's nice about it, it's an equation for a straight line, and the slope is the heat of the enthalpy of vaporization divided by R, the gas constant, 8.314. So just by measuring pressures and temperatures and changing the temperature and measuring the new pressure, and then plotting that, we get the slope of the line. Since we already know R, we can get the enthalpy of vaporization. Another useful equation for Clausius-Clapeyron is this one right here, where if you had a gas at a certain pressure and a certain temperature, and you said, okay, I want to increase the temperature, I wonder what the new pressure of this gas will be if I increase the temperature. This second equation down here does a good job of calculating that. The natural log of the pressure at any time 2 divided by the pressure at any time 1 equals negative delta H vaporization over R times 1 over T2 minus 1 over T1. And so that's another nice way of finding out new pressures if you want to know when you change temperature. And that's also, if you have a gas, you could measure at a certain pressure and a certain temperature, P1 and T1, increase the temperature and note that the pressure increases, measure both those, and it's another way to calculate delta H vaporization. Now, the linear way using a line is better because it gives you many more data points to average out to get a much better result for your delta H vaporization. But this one can be used, and there's a nice example in your book. I'm sure if I were to give you T1, T2, and delta H naught vap and P1, you could calculate P2. All right. So we're going to be kind of going through the book a little bit at the end because they've got some nice pictures in here. The next thing they talk about that we're interested in is the critical point, and I'm not 100% sure why they're including critical point at this part, but okay, I would leave it for another 5 minutes. But the critical point is when you can get a supercritical fluid. So if you increase the temperature and increase the pressure enough, you get a system where for some molecules they turn supercritical. And here's kind of an example of what that would look like. Here you have just a normal temperature and pressure. Here is a liquid, and then there's the gas, the vapor above it. As you start increasing temperature and increasing pressure, we see that weird things are happening. Look here where the liquid and the gas above it looks very much like the liquid, until you get this point here where you're supercritical. You have a supercritical fluid where one could kind of look at it as an extremely dense gas, or maybe not quite a dense liquid. It really has properties of gases and properties of liquids. It can flow like a liquid, but it tends to dissolve things much like gases dissolve other gases. So it's a really interesting state of matter, this supercritical fluid, and has certain applications, for example, making decaffeinated coffee. Turns out caffeine is really soluble in supercritical carbon dioxide. But it's a weird state of matter that has kind of gas properties and liquid properties. It's like somewhere in between there. All right. So, the next two items in the book are stuff we've already covered, so we don't have to spend hardly any time on this, but we remember that if you have a solid and a liquid and a gas, the processes going in between those. Solid to liquid is melting, liquid to solid is fusion, liquid to gas is vaporization, gas to liquid is condensation. Recall, solid to gas is sublimation, and then gas straight to solid is deposition. Also in this chapter, and something we covered extensively in the thermodynamics chapter, just because I think it belongs there better, is the heat of vaporization, heat of fusion, the changing of state going from, say, ice at minus 10 degrees to water, steam, gaseous water to 110, or excuse me, ice at minus 10 degrees to water at 110 degrees. It's the heating curve for water. Note, we did those calculations before, so that should not be a problem for you. In the book, they have nice examples of that and working your problems, and you can look at those. We've already covered that, though. The last thing, and pretty important part of this chapter, is something called phase diagrams. And phase diagrams just show you, okay, as you have a substance and you want to look at the pressure and temperature relationship, what's going to happen? And so here's a standard phase diagram right here. It is a phase diagram for water. And what we see here is it's this box right here, and we've got some lines in here. Note, this axis is pressure, so as we go up, pressure is increasing. This is temperature. As we go to the right, temperature is increasing. And we have these lines on here, which means if we're at room temperature and normal atmospheric pressure, so that's 760 torr, 1 atmosphere of pressure, and we're at room temperature, which is about 25 degrees Celsius, we follow these lines, 760 torr this way, 25 here. We see water is a liquid at this place, at this temperature and pressure, because this represents water would be a solid under these temperatures and pressures, liquid here, and a gas down here. Okay. There are a few things to note. Note, as we look at this, if you're going on this line, what happens if we are at 1 atmosphere of pressure and 0 degrees Celsius? We're right on this kind of vertical line here, and that is the solid to liquid transition. So what it means is if you are actually at 760 and 0 degrees, then you have two processes happening. Solids are melting to become liquids, but at the same time the liquid is fusing to become a solid. Both of those processes are happening at the same time. It's an equilibrium. If you keep the pressure at 760 torr, you keep the temperature at 0 degrees Celsius, both those processes are happening. Just like if you keep the pressure at 760 but increase the temperature, so going this way we're increasing temperature, you'll get to this line. And if you find yourself on this line, or the system finds itself there, that is the demarcation between liquid and gas. And so if we're at this point on this line, that means liquid is vaporizing to form gas, but at the same rate, as long as we keep our temperature and pressure constant, the gas is condensing back down to form the liquid. Both are happening at the same time. And what's interesting is right down here we have what's what we call the triple point. So what's happening if we were at this exact temperature and this exact pressure for water? You'd be at the triple point, which means all processes are happening. Solid is melting to form a liquid, but at the same time the solid is subliming to form the gas, and at the same time the gas is condensing to form the liquid, and the gas is depositing to form the solid. All things are happening at the same time. And the liquid is forming the gas, gas forming the liquid. All three of these processes all going on right there. If you happen to find that exact right pressure in that exact right temperature, you'd be at the triple point. Also look here, we find the critical point, where if you're a liquid and we're at this pressure, if you increase the temperature, you'll come past this critical point, and past this critical point, you don't really have a liquid or a gas, you have this supercritical fluid up there. All right, now it turns out water does not easily become a supercritical fluid. However, carbon dioxide does. And if we look at the diagram for carbon dioxide, which is this one right here, what we see is, if you know anything about carbon dioxide, it's also known as dry ice. At 1 atmosphere of pressure, at the temperatures of dry ice, but at 1 atmosphere of pressure, you know that dry ice is a solid. If you increase the temperature, note we are below the triple point, which means we eventually go from the solid to gas areas, which means dry ice never melts. At 1 atmosphere of pressure, you can never get dry ice to form a liquid. At 1 atmosphere of pressure, it's either a solid. If you increase the temperature, it becomes a gas. It sublimes. And that's its story. It's because of where the pressures are of 1 atmosphere on this phase diagram, solid dry ice or gaseous dry ice, we will never see it in a liquid. Now, you could see it in a liquid if you took that carbon dioxide at 1 atmosphere, increase the temperature to about right here, 0 degrees Celsius or so, and then increase the pressure. Now you got to increase it way up here. You're going to have to increase it to like 50 atmospheres of pressure, but then you might see liquid carbon dioxide. And note, above 72, roughly 73 atmospheres and above 31 degrees Celsius, you get the critical point. You're above the critical point of carbon dioxide, and it becomes a supercritical fluid. All right. Now, there's an interesting thing when we look at these phase diagrams here. And when you look at carbon dioxide, it turns out the phase diagram for carbon dioxide, above it is a phase diagram for iodine. These are how most things behave, and the way it works is when we look at from the triple point going up, the solid to liquid line, note that it is sloping a little bit to the right, just a little bit to the right. Iodine slopes a little even more to the right. What that means is, say you have iodine at 184 degrees Celsius and low pressure, it would be a gas. You increase the pressure, keep adding the pressure, one would expect that the iodine vapors would get closer and closer together, and they do, to form a liquid. And if you keep adding more pressure, we would expect it to become a solid. And that's how most things work. That if you keep pressure of a gas constant and you keep temperature of a gas constant, increase pressure, it goes from the gas to the liquid, then the liquid to the solid. The interesting thing about water is when we notice the phase diagram for water, the line goes to the left a little bit. So if you had water at about 0 degrees Celsius or so, and you, at very, very low pressures, it would be a gas. And if you increased the pressure, it would go from the gas to the solid. And if you increase the pressure more, keep increasing the pressure, it would go from the solid to the liquid. Water is this weird thing that increasing the pressure will make it go into the liquid, because it turns out that at very low temperatures, close to 0 degrees Celsius, liquid water is more dense than solid water. So adding pressure really packs it together, makes it more dense, and it becomes a liquid. Because liquid water is more dense than solid water at 0 degrees Celsius, this is why ice floats on water, which is very important to you if you are a fish in a pond in the northern United States or in Canada, because since the ice floats, it stays at the top of the water and the fish can swim underneath it just fine. If water behaved like the other compounds, where the more pressure you added to it, it would become a solid, then the solid would be more dense than the liquid, the ice would sink, and pretty soon the lakes and rivers would just be completely ice packed. There would be no water at all, and all the fish and all the other animals will die. All right, that good news. That ends this chapter. Only one more chapter to go, and bad news, it's really, really short.